projects.
That makes them go faster. And Asher is going to tell us a bit more what they can do for the rest of us, right?
Yeah.
Yeah, thank you.
But before I do, if you like the look of Key, come to the Key workshop tomorrow. I can assure you it's going to be very good. I promise. So I've tried to meet as many of you as I can. I don't think I've met everybody just yet. Can you all hear me from the back?
What?
I'll take that as a yes. So before I tell you about what vectorized trees can do for you, my name is Asher. Just a few months ago, I graduated from the University of Warwick over in the UK. And a couple of years ago, I was the intern at Dyalog, one of the interns at Dyalog. I enjoyed it so much that I came back the following year as the senior intern, which was my official title. And now, as of this morning, I'm a proper employee. So hopefully this won't be the last you see of me, fingers crossed. And what I want to talk about today is something that I was doing while I was senior intern. I got really interested in these tree structures that feature in the Co-dfns and the static analysis. And in order to understand them and fill the gap in understanding that I think is out there, I wrote a tutorial about them. So this is me presenting that tutorial at the last user meeting. That's a man who hasn't had to do his final exams yet. And I talked a lot about how I made this tutorial, the tools I used, the style of it, but I didn't get into the content. Just at the end, I put up a link and I said, go and read it, please. And I'm sure lots of people did go and read it, hopefully. But I don't think everyone has. So what I want to talk about today is some of the meat of it, how the tree stuff actually works. And also some details about when it's good, when it's not so good, whether or not it's going to be useful for you. So trees are these things. Anytime you've got hierarchical data that you can organize somewhat like this, you might have a tree on your hand. So for instance, the file system is a really good example of a tree, because you can have folders that contain other folders that contain files. Anytime you've got data that's contained inside other data, or data belonging to other data, you might have a tree on your hand. Interestingly enough, a family tree doesn't count, because typically you have two parents in a family tree. But we're talking about cases where you will have either one parent or no parents if you're at the very top. So even though family trees don't count, we are going to steal some of that terminology. So for instance, this bit of data here, this node is what we call them, could be the parent of this piece of data, which would be its child. We're also going to steal some terminology from the tree metaphor. This node at the very top is going to be the root. It's the foundation of the whole thing, it's the root. And these nodes at the end that don't have any children of their own, these are leaves. Because you can imagine they're at the ends of the branches, there's nothing else branching off them, so they're leaves. And in most applications that have trees involved somehow, the relationship between parents and children is going to be the parents reference their children. And there's a number of ways this could be set up. It could be that your parents are namespaces, and then the children are members of that namespace, or they're nested arrays, and the children are the elements of that array. Whatever the setup is, the parents are pointing to the children. The trouble with that is if we want to work with any of the data we have to start at the top of this structure and then go down one item at a time, maybe work our way back up, go down again. And we're working with one piece of data at any given time. We don't get the opportunity to make use of the APL primitives and work on our data in batches all at once. So the way that we can warp this setup a bit so that we can get to that point is to invert this relationship. So instead of parents referencing their children, if the children reference their parents, then something interesting happens when we rearrange the structure of the tree so we can put it into an array. So what I'm going to do now is I'm just going to rearrange the placement of these nodes. We've got exactly the same tree structure here. All we've done is moved all of the nodes so they're on a big straight line. You can imagine if I picked up this node and lifted it up, everything would fall down into the same place it was before. And now if we try to put this into an array, here I'm in quad IO 0, sorry. You can use quad IO 1, it works just the same.
Don't apologize for being right.
I'm not going to wade into this debate. I like both. Anyway, so if we put this into an array like this, the only thing we need to store for every piece of data to encode all of this structure is where a node's arrow is pointing, so where its parent's going to be. And since we've put all of these nodes into the array, we can associate those with the indices into the array. So if we put the numbers of them in there, now we've got the whole structure of the tree represented by just the numeric vector. So all of these 5s here are because all of these nodes, their parent is this node, which is at index 5, and so on and so on. The only wrinkle in this is that the root of the tree doesn't have a parent of its own. It's just kind of dangling there. And there's a couple things you can do. Yeah?
Is this also what is sometimes referred to as actor trees?
Yes, this is exactly that. At some point, I should have a slide later on of sources, and Stephen Apter's article is one of them. It's really good. So we're missing a parent for the root node. The convention I like to adopt for that is to have a self loop, to have the root node say that its parent is itself. You don't have to do that, but if you do it that way, some things practically turn out a bit more useful. So we're just going to put a 0 in there, and then there's an imaginary arrow, as if that's its own self loop. It's not really part of the structure, but we have to put something there. So that gives us the structure of a tree. If we've got a tree like this, then we have a parent vector that looks like that, and we've encoded the whole structure. The thing we're missing here is any data. All we've got is the structure of the tree, and we can't fit any data into the numeric vector along with it. So where are we going to store that? Luckily, we already have indices of the nodes associated. We have indices associated with the nodes of the tree. So we can use those same indices to index a different vector to get whatever data we want out. So for instance, I've labeled the nodes here with the letters of the alphabet. I can just have a labels vector that has the data associated, and these indices line up. So the root is labeled A, so it's this 0th entry in both of them. So this gives us an inverted table structure. If you want to know more about inverted tables, come to my workshop tomorrow. And this stuff works really well. Let me show you a little bit of code now. Just a little bit, I promise. And I don't want you to necessarily understand all of this code in detail. I just want to get some vibes across to you. The message I want to get across is that we're not doing some explicit traversal of the tree structure. We're just using the APL primitives to implicitly look at that tree structure. So I should have this up here. Yeah, there we go. So here in the session, I've got my parent vector, I've got my labels vector, and then this is a little utility function I wrote, ppv, that's pretty print vertically, which is going to take a parent vector, and it's going to print onto it the structure. It's going to print the structure, and it's going to print onto it the labels that we're giving as the left argument. And there's various things you want to do with trees. There's lots of things you want to do with trees. You've seen some of them already today. Something simple you might want to do is work on just the children of some nodes. So for instance, I might want to work on just the children of nodes B and C. So how am I going to find a mask to get all of those out? It's quite simple. All we have to do is look up, first of all, what are the indices associated with B and C, and then which nodes are reporting those indices as their parent. So we just look that up in the parent vector. And then that gives us a mask, and if we print that mask on, indeed, we have these 3 nodes, which were the parents of, the children of B and C. Yeah?
Is there a way to easily do a recursive of that, like the bottom 3 as well being included?
You have read my mind. That's coming in just a second. So similarly, you might want to look at editing the structure of the tree somehow. So we already, say we've got this tree here that's descending from node C, this sort of subtree here, and we want to break that off somehow. We're not interested in it being a child of A anymore. We want it to be its own thing. We already know that to indicate a root node, we have a self loop, right? A node is saying, I am my own parent. So if we set that for the node C as well, that is going to edit our structure. So if we look up the node C, we find the index of it, that's I, and then we set it to be its own parent, that breaks off the tree. And then something you might want to know, for instance, is all of the nodes that are descending from a particular root. This is quite similar to what you want. So if we wanted to figure that out, we can start from a node and we can move up through the parent pointers until we get to a root. And once we get to a root and then keeping going up, we're just going to loop on ourselves. Then we know we've reached a root. So if we do that indexing for every single node in the tree, we're then going to discover what are the nodes, or the roots for each node. We print that on. Indeed, all of these descend from C. All of these descend from A. If you're doing this in something where you don't have them separate, you can add checks and stuff so that it doesn't stop after a certain point. Cool, so this works, is the point. But when is it useful? And in my opinion, there are about 3 criteria for when using a parent vector is going to help you. First of all, oh, yeah, there we go. When your trees are large, that's going to be good, because we get a performance gain by moving from the nested representation to the parent vector representation, because we're moving from operating on one thing at a time to using the nice optimized primitives that are written in C on all of the data at once. And when you've got a larger tree, moving from that nested representation to that vector representation is going to give you more of a performance gain. You're also going to be helped when the trees are irregular. If you've got a data that's coming in that has a kind of tree structure, but you know what it's going to be ahead of time, you might not need the complexity and the generality of the parent vector representation if you can just slice and dice things up because you know exactly where it's going to be. But if you've got data that's coming in and has any shape and you don't really know what it's going to be, then you need the generality of this representation. And as we saw a second ago, it's really useful with the parent vector representation to be working from the bottom up, because you can index with your parent vector to go one level up the tree. So if you've got a problem that can be solved like that, that's ideal. Sometimes when you look up algorithms for working with trees in books or online, they'll give you a solution that works from a top-down traversal, where you're starting at the top and you're working down. Sometimes, not all the time, but sometimes you can reconfigure something like that so it's actually working bottom up. So this is possible more often than you might think. Not all the time, but more often than you might think. So now let me show you some examples of where this has been used in the wild. The first one you've heard of is Co-dfns and the static analysis. These are really, really cool projects. They're the reason I got interested in the tree stuff in the first place. And they're perfect suits because your code is represented as one of these trees with a parent vector. Your code can be large, your code can be any kind of shape, and if you go and look in the code, they're doing these bottom-up traversals all of the time. So that works really well. I won't tell you more about that. You've already seen it talk about it today. I did think, after I finished learning about trees, and after I'd learned how Co-dfns works, is this just a trick to make Co-dfns in the static analysis faster, or can we use this for other things? The answer is yes, we can. So for instance, we already talked about the file system being a really good example of a tree. And it's also really suitable for working with parent vectors, because your file system can be large, it can be irregular, and as we're going to see in just a second, you can do all sorts of queries on your file system structure quite easily by representing it with a parent vector. So say we've got this file structure. The specifics of this are not important. This is some random file structure. There's all sorts of questions you might want to ask about this. One of them might be, tell me all of the files, give me the names of all the files which are larger than 100 kilobytes. That question doesn't really care about the fact that this is a tree. We're just asking about list of all the files that are in here. Tell me which ones are bigger than 100. And what's nice about the parent vector representation is when we don't care about the tree structure, we don't have to think about the tree structure. So the way you actually figure this out is you just take a mask of all the files, all the nodes which are files, a mask of all the nodes which are as big as you want, and then use that to filter out the names that you want. No mention of the parent vector, because we don't care about the parent vector for this question. If you were using the nested representation, you would have no choice but to start at the top and work your way down and mess with the structure of the tree when you don't care about it for this question. Sometimes, of course, we are asking questions where we care about the structure. So for instance, in this tree, say I want to know who is using all my disk space. I'm looking in my desktop and I'm seeing I've got my drawer, I've got my wallet, I've got my plant pot, who's using all of my hard drive. The way if I want a report of the space that all those top-level members are using, I've got to look at the sizes of all the files contained within my folders and sum them all up to the very top. And the way you figure that out, again, I don't want you to understand all this code. I want you to focus in on just one specific line. This gives me a nice report of the disk usage. And the way that we're building up this sum of all of the nodes underneath is on this line here, where we've got one level of the tree. We've got the usage of one level of the tree, and we're adding that usage to the usage of the parents of that level. And all of this is happening in parallel. So because we have the parent vector available, we're able to do this bottom-up traversal really easily, and because we're doing a whole level at once, that's going to be a lot faster than just working down one node at a time. So for data, parent vectors are good. If you've got something concrete like a syntax tree or a, yes?
Wouldn't it be better to map it to the parent node and then use key?
How do you mean?
Well, instead of doing it would compute the top level parent that you did earlier? Or
You can.
And then use key to sum the. Never mind.
You've got to do multiple levels, so it has to work recursively up. There are versions of this that use key as well, but because modified gets can handle some keying behavior on its own, we don't need it for this example. I'll tell you more about it afterwards. So for data, this stuff is really good. But I've just come off a computer science degree. Computer scientists love to use trees, not just for storing their data, but also for accelerating their algorithms. And I came away from working with the trees for all sorts of data stuff and thought, can we use it for the algorithmic stuff as well? And the answer to that question is more in the middle. It's yes and no. I'm going to show you a no answer first. Any physicists in the audience might like doing gravity simulations like this, where we've got particles that have a gravitational effect on each other, and we're simulating these could be galaxies or something. And the naive way of doing that is to basically just do a big outer product. Each particle has to compare itself to every single other particle, find the vector difference, and then do the force calculations. And that works well, but it's going to be slow if you've got lots of particles on the go. So there is a way that physicists like to speed up this kind of calculation. And believe it or not, it uses a tree. If you can imagine splitting up the space into 4 quadrants, and then splitting up those quadrants into quadrants again, we have a kind of tree structure of that splitting up that's going to look something like this. And the idea is that to calculate the force acting on a particular particle, we don't want to compare against all of the particles. So we might, if we're looking at this particle, start at the top of the tree and say these subtrees over here, these quadrants of the space, are far enough away from this particle that we don't need to think about all the detail. If we just approximate those particles by larger particles, larger sort of virtual particles that are far away, we're going to get basically the same result. And then this gives us fewer particles to do our comparisons with, and presumably it will be faster. So you've got to do that for every single particle. You start at the top, you come down, and you approximate as you're going down. I coded up both versions of these to see if it actually did give me a speed up. I was really hoping it would. This is the naive version, so this is just working with a great big outer product. And this is the optimized version. It's much slower. There's 2 possibilities for this. One of them is that I did it wrong, which is it's always a possibility. When you implement an optimization, it slows things down. Maybe you just did it wrong. The other possibility is that the interpreter overhead from doing those top-down traversals is overwhelming the speed up that we get from doing fewer gravitational calculations. Because for every single one of these particles, we have to start at the top of the tree and go down. There's a lot of overhead from that DYNA function, or it could be a transform, whatever you implement it as, working one at a time for every single path going down the tree. It's horrible. And it might be that when you have more particles, that relationship is going to invert, and actually it will start being faster. My laptop is not strong enough to try. This thing does not even have a HDMI port. But that's beside the point. The point is that using a parent vector here did not speed us up because we had to do a top-down traversal. Parent vector really helps with doing stuff that's going bottom up. Doing the top-down didn't help us. It didn't make things worse. It was neutral, but it didn't help us. That's not to say that it's never helpful, though. Another example I want to show you is working with a disjoint set kind of data structure. If we've got some data points scattered around like this, it's supposed to look vaguely like a face. It was the best I could do in the airport. We might want to group together these data points into the eye, and the mouth, so that they're non-overlapping. And the way we might do that is we might go through and assign categories, and if we find a data point that's already close to an assigned category, we'll assign it to the same one. So we'll get a situation kind of like this. But we reach a problem when we're looking at a data point like this that's kind of close to 2 partitions that we've already assigned. So which one do we add it to? Ideally, of course, as humans, we can see that the mouth is all going to be 1 partition. We don't want there to be 2 separate ones at all. So what we need to do at this point is assign everything to just one of the partitions. And we want this operation to be efficient, because when we go all the way through and assign all of our different data points, we might have to do that union operation quite often, and we want that to be quick. And surprisingly, well, no surprises actually, the way that we make that quick is by using a tree structure. If we associate with each one of those partitions a tree, and we just identify it by its root, Then when we need to merge these things together, the only thing we need to do is reassign a couple parent pointers. That's it. There's more to it than that, but that's the gist of it. And then we can forget about the information we had associated with those before. That's how we make that operation really efficient. And the key thing is here, we care about the parents. We don't care about who your children are. We care about who your parents are when we're doing this operation. So we can use a parent vector for this, and it works really well. I came across this when I was finding contiguous regions of an image. I was using this earlier on this year. But it turns out you can use it for all sorts of things. You can find connected components of graphs. You can find minimum spanning trees of them. According to Wikipedia, you can solve symbolic expressions by unification. I barely know what that means, but it sounds cool. And probably more stuff. So point is here, this is an algorithmic application of the parent vector stuff, not for storing data, but for accelerating algorithms somehow, where the parent vector also works. Right, so for data, it's great. We can do syntax trees, we can do file systems, we can do more stuff. For accelerating algorithms, it doesn't work for everything. It didn't work for particle simulation. There are other things it's also not really suited for, not least because sometimes you use trees because you haven't got all of your tree calculated yet, and that's why you work from the top down. But for something like the disjoint set stuff, where we were going bottom up, we were using those parent pointers, it works really well. So you can do trees the APL way. If you have trees that are large, that are irregular, that you can often traverse bottom up, which you might be able to do more often than you think, consider giving it a go. You might speed up your program. You might make it easier to understand. I personally find some of that stuff a bit easier to understand when it's in that parent vector form as opposed to with the traversals. But your mileage may vary. You might run into a problem that you can't accelerate with parent vectors. But give it a go. If you're interested in learning a bit more about it, go and read my tutorial. It's really good. I read it myself when I was preparing this talk, and I was like, wow, he's a really good writer. And now I've got time for questions. Thank you. Yes?
Is it possible to extend this kind of thinking to graphs as well, or something that isn't strictly a tree?
The reason that this works well for trees is because we don't have to use any nesting when we're building up the representation, because everything only has to think about, oh, it'll take me ages to get back to the diagram. There we go. Every item of data only has one thing. We only have one number associated with it, so we get that. The analogous thing for a graph would be to have a list of connections that you've got, and that's just the usual neighbor list representation. Something I do want to do at some point is work with the, what's it called, the CRC format for sparse matrices. You can do some really cool stuff with graphs if you have a dedicated data structure for working matrices like that. That makes things like the transitive closure idiom not run in quadratic time, but actually run much faster. I don't know. Please let me do that at work. Yes?
Oh, you can go first.
There's a kind of a fun little regular language construct called the Brzezinski derivative that's like a tree of regular expressions that I like playing with.
Mm-hmm.
And you mutate the tree, you mutate the nodes in order to sort of perform a regular expression. Is it possible, you had an example of mutation which was reassigning parent.
That was a simple example of the mutation.
Is there an application where we can actually sort of like add nodes or remove nodes?
Oh, absolutely, yeah. The simplest case for adding nodes is just appending to all of your vectors.
Mm-hmm.
But you can do things in a lot more complicated ways as well. I don't think I have the resources to show you right this second, but yes is the answer.
Okay, cool.
Yeah, there's this really simple algorithm for node deletion as well. I mean, once you have those two, everything else kind of falls out.
Yes, Max.
Is there system function support for this format, like with inverted tables?
Some system functions have support for inverted tables and some of them don't.
So what about for this after tree? For example, can I get an after tree out of a quad info variant one?
Possibly. I'm not sure. I don't remember the details of quad n info. What I will say is.
It's a file tree. It returns a file tree.
Maybe. And if we can't, maybe we should. I would be opinionated like that. You can, in Quad CSV gives you inverted tables quite often, so you can have something coded like that. Something I also did in the tutorial itself is go through an example with Quad JSON, because Quad JSON has the matrix output format. And if you just transpose that and pull out the rows, then you have the inverted table structure. And it's very, very close to what you want.
Can JSON be viewed as a tree as well?
Oh, absolutely. Anything where you have a relationship of like, I am contained in something or I belong to something, you've probably got a tree on your hands. So it could be that you've got a root object and these are the named members, and then maybe one of them contains an array, and the array contains 3 items, something like that.
So did your board cover how to transform an output of a quad JSON into a tree?
Yes, it does.
Okay. Cool, that's it.
Cool.
I think Aaron had his hand.
Yes, sorry, Aaron.
You're good. Probably that's the last one, I'm afraid.
I wanted to answer the question about graphs. So
Mhm.
a lot of times, real-world graphs aren't fully general graphs, and it's very often the case that you can overlay multiple trees on top of one another to get the graph that you actually want.
Ooh.
And so that's something that we do in the compiler, is we have certain data structures which are technically graphs, but they're represented as a single parent vector because the edges never conflict with one another. So they're actually 2 trees overlaid together as a form of graph.
Cool.
We effectively have a DAG, right? And it's just where 2 trees are related.
Tell-
One of the nice things that, I mean, you kind of touched on this, so you can forget the tree structure. You can do this because all of your data is just shared, and since the tree structures, the graph structures are orthogonal to it, so all this data sharing can be used for free.
Great.